Good morning. This is the first segment of section 7.3. In all likelihood, we'll end up doing three segments because in the first segment, I'll derive what's called the law of cosines, and that may take a minute. Then I will likely do an example of a side angle side triangle solution involving that. And then probably in the third segment, I will do a side, which will be relatively straightforward. So the first two segments will be a little bit longer, and probably the third one will be kind of bang up, although I may make some conversation in the end there. So let's let's move over here to the document camera. What I'm going to do is I'm going to create a setup where we, and this is actually kind of a little bit of a complicated derivation, but I'm going to try to prove to you the law of cosines. And remember, we've done this before where we create two equations and then we solve for two unknowns, and it's a similar sort of setup, except it's a little more complicated than the last one. So this is section 7.3, page 1. Okay, so let's start with, I mean, it really doesn't matter if we have an acute or an obtuse triangle, but I think an acute triangle makes it a little bit easier to see. So let's suppose that we have a triangle, and it's not isosceles, but it makes for good TV when you do that. So here's let me do some labels here. Let me make this. I want the x to be here. So let me make this A, and this B, and this C. So that makes this side little c, this side little b, and this side little a. And I'm going to, just like we did in the previous derivation for law of, well, we didn't do this for law of sines, but the altitude is kind of a way to equate two sides of this triangle. And as you may remember, previously when we were developing the sort of whale problem in section 2.5, we did this little thing where we kind of broke something up and we said, well, we don't really know what this value is, but I'm going to call it x. And it's a very similar sort of derivation. So what I'm going to do, the whole length is b, right? But I'm going to break this up into x over here. And on this side, then, this will be b minus x. Okay. So what I'm going to do now is I'm going to use a combination of the Pythagorean theorem and the definition of cosine to solve this triangle, and eliminate x from the equation, and then have a relationship between the three sides and an angle. That's sort of the big picture. So starting with over here, let me do the easy one. So I want to relate h and x with this angle, and so what I can do is I can write the Pythagorean theorem. So I'm going to first state that x squared plus h squared equals c squared. And so the result is that h squared is equal to c squared minus x squared. Now, simultaneously, I'm also going to write a relationship between the cosine of angle A and x and c. So this gives me, in some sense, I'm going to find a way to substitute x. So I really have sort of three equations. Okay, so note that cosine of A is equal to x over c, and therefore x is equal to c times cosine of A. Okay, we'll end up substituting that at some point. Now let's focus back on this triangle, this right triangle. For this right triangle, I can write a relationship using the Pythagorean theorem between this side, and this side. And that's exactly what I'm going to do. So I've got b minus x quantity squared plus h squared is equal to a squared. So just like I did in this first step, I'm gonna have this equal to h squared is equal to a squared minus b minus x quantity squared. So I'll go ahead and distribute the, should I distribute it out? Sure, let's do that. So this is a squared minus b squared plus 2bx minus x squared. And that's, I mean, you can go back and verify that. You FOIL this out, you get b squared minus 2bx plus x squared, and then the negative sign comes through. So now what I'm going to do is I'm going to relate equation number 1 with equation number 3. So the right-hand side of this, equation number 2, will be equal to the right-hand side of equation number 1. And I'll go ahead and write that down here. So c squared minus x squared is equal to a squared minus b squared plus 2bx minus x squared. Now, notice that we've got a minus x squared on both sides of this equation, right? So that will cancel because x is some non-negative number. We can just subtract or add or subtract from both sides. And I'm going to do a little bit of rearranging here. So what I want is I want to move this. I want to get a squared by itself, just because that's how the formula looks pretty good when you do that. So I will move everything else to this side, but I'll have a squared equal. So a squared is equal to, we'll notice b squared will become positive. C squared was already positive. And then when I move this to the other side, I'll have minus 2bx. Okay. So this is starting to look a little bit like the Pythagorean theorem, and it should, because the Pythagorean theorem is a limiting case of the law of cosines. But there's this extra little term in here that kind of throws things off. So what I will do now is go back to this equation where it's a substitution for x, and I will plug it in right there. And so what I end up with is a squared is equal to b squared plus c squared minus 2bc cosine of a. And this is the so-called law of cosines. It's one version. I'll call this maybe version 1. And there's actually 3 different versions because the labels for the sides and the angles is arbitrary, right? So we could just as easily say, well, you know, there's another equation that says b squared is equal to a squared plus c squared minus 2ac cosine of b, right? You see the cycle here, the 2 sides and the other angle, 2 sides, the other angle. Or you have c squared equal to a squared plus b squared minus 2ab times cosine of c. So this, all 3 of these are true no matter the labels. The only thing that's critical is that the labels have to be angles and their opposite sides have the same sort of designation, b and the opposite side b. So like I said, this is version 1, which is used when you have 2 sides and an included angle. You can find the 3rd side. That's kind of the strategy there. So 2 sides and an included angle, side angle side, gives you the 3rd side. So that doesn't solve the entire problem, but then what you can do is you can look at what's called version 2, where you're actually solving for the angles. Now, if you are solving for the angles, if you rearrange this equation and get cosine by itself, what you end up with is cosine of a, and I'll let you do the algebra. is equal to b squared plus c squared minus a squared over 2bc, b times c. Now, there's a situation where you've got, and this may be a little bit difficult to remember, but notice this is the angle in question. It's the only thing over here that's negative. It's got something that looks a little bit like the Pythagorean theorem, and you've got this kind of cross term below. So if you're trying to find angle A and you have all three sides, so this is side, 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 then you can find this angle by simply taking the inverse cosine. So A will be equal to the inverse cosine of this mess. And you may be asking yourself right now, you're like, but wait a second, didn't you say when you take the inverse trig function, you got to be really careful because you may be dealing with range errors or whatever else. Well, it turns out that the range for inverse cosine happens to be 0 to 180 degrees, and that's very convenient because that's all the possible angles that you might get out of a triangle. This ratio in here is potentially positive or negative, but you'll never end up with a situation where it's greater than 1 or less than -1. And in fact, if it is equal to 1, that's because this numerator is actually 0. And if the numerator is 0, this is the Pythagorean theorem. It just reduces down to it. So we will talk more about the sort of principle and the alternate roots of the cosine function later in chapter 6. But for the time being, you can take my word for it, this will always produce the correct angle. You'll never end up with anything that's weird. So to kind of finish it out for the other two versions, angle B is equal to the inverse cosine of, and it's the other two sides, so a squared plus b squared, or sorry, a squared plus c squared minus the associated side squared divided by 2 times the product of these two sides, so AC. And then finally, if you want to find angle C, this is the inverse cosine of the other two, so a squared plus b squared minus the associated side, c squared, divided by 2 times the product of the adjacent sides. So this is what's called, between these three, and I know I've spread it over to another page here, but these three versions, or these three different cycles, are what are called version 2. So version 2 is when, and it's not a formal term, it's just, it's kind of how I'll refer to them in the future. But basically, if you have all the sides, you use these equations to find the angles. If you have side angle side, then you use the other equation, the other version to find the remaining side, and then you cycle back to these. So these are actually more useful in most cases. The only thing that you have to be careful about, and I'm going to just state this right here, if you have either side angle side or side side side, you need to use the law of cosines, any one of its form, only. Now, it's not necessarily true. You could revert back to the law of sines. However, I want you to kind of think about this progression. So if you had a situation where, let's say you had, let's say you knew let's say you know a side, you know another side, and then you know an angle. Okay, this is side angle side. And what would you do first? Well, you apply the law of cosines and you find that third side. right? So at some point then you would find this side. And now it's very, very tempting to use the law of sines because you have an angle and its opposite side, right? But I want you to look at what situation that is. Either if you use those two sides to find this third angle, this angle, or if you use these two sides to find this angle, both of those situations are the ambiguous case. So it leads to the ambiguous case of law of sines, right? And so this is why you do not want to do this. The ambiguous case, then you have to go back in and think, okay, well, is it a situation where it's an acute angle, it's an obtuse angle, and maybe you can't even determine that because that information is not necessarily given. You'd have to solve both triangles, which most people won't do. So it's quite possible that you can create a solution that's not true. However, if you use these equations, these version 2 equations, to find this other angle or this other angle, there's no problem. So that's just kind of my statement there. Once you start down the path of using the law of cosines, do not suddenly shift over in the middle to the law of sines because you almost, it's not that it will always happen, but you know, it's a coin flip. Half the time you'll be right and half the time you'll be wrong. So it's better just to be right all the time. So that's kind of my pitch for the law of cosines. For this first segment, I think we'll call it quits here. I'm going to come back in the next segment and show you the side angle side situation and actually show you where this problem occurs. And then, and I'll have to kind of doctor up a situation that gives me that. But we will see you here in the next segment.